Okay, here's another question that came off of exam number 4. Um, then I'll continue working through some more problems here. So at STP, how many molecules are present in 3.55 liters of pure carbon dioxide gas? Um, Pretty straightforward problem. Right here you'll see the 3.55 liters of CO2 at STP is going to occupy, for 1 mole of it, it's going to occupy 22.414 liters. So this will allow you to go from liters of CO2 to moles of CO2. And since molecules are representative particles, we use Avogadro's number to calculate the number of representative particles. So once we have mole of CO2, 1 mole of CO2 is going to be Avogadro's number of CO2 molecules. So then you just multiplying across the top and dividing by the bottom, and you get 9.54, 3 sig figs, times 10 to the 22 CO2 molecules, which that number should be less than Avogadro's number at STP, and it is, because this is not 22.4 liters. So it's less than what a mole would occupy, so you should expect to have less than a mole of CO2 molecules. On this problem, you had to calculate the ratio of the rate of effusion of methane compared to dinitrogen monoxide under the same temperature and pressure conditions. And then when describing the rate, round your answer, your answer to 1 decimal place. That's important for this problem. Reason I underlined it there is because the first time I worked it, for some reason, I did it with the actual sig figs based on the molar mass, but then I realized that I had put 1 decimal place. So you're comparing methane to nitrous oxide here, N2O. And you use your rate formula that I gave you in class. You want to put what it says in the problem, the rate of methane versus N2O. So you write it in that way. And that's equivalent to, and then you switch the places. So the square root of the molar mass of the N2O over the square root of the molar mass of the CH4. Then I just used a periodic table to get those molar masses, and then divided that and approximated it to 1 decimal place of 1.7. Now the way to word that might be, therefore CH4 effuses at a rate 1.7 times greater than that of N2O. So it's smaller, lighter. It's a lighter weight molecule. The molar mass is smaller. So it's going to be a little bit faster at effusing through a barrier than N2O might be, based on that prediction of the rate. On this one, you have a sample of gas that completely fills a vertical airtight chamber, and you're asked to calculate the final temperature based on these other variables changing, and then round your answer to 2 decimal places and report it in degrees Celsius. So remember that when you do the calculations mathematically, you need to use Kelvin. So this standard temperature, you're going to use a Kelvin temperature for the calculation, and then I want it in degrees Celsius, and I want the 2 decimal places that go with it. So it's a combined gas law problem where you're solving for T2, the new temperature. So there's the equation you ultimately end up with. Then I wrote down my givens on the left, and in Kelvin, this is going to come out to 388.16 Kelvin. But then you got to take away your 273.15, and you get 115.01 degrees Celsius over here for an answer. So the tricky part, I guess, is making sure you substitute in the correct place, and I believe that I did so on that one, so that you, for P1 and T1 or P2, T1, and V2. So I use my standard temperature, my second pressure, right here, and 600 liters was my second volume. Original, I went ahead and used torr because of the other pressure being in torr. So I used STP, so standard pressure, 760 torr, and then the original volume was given as 500 liters. And you get 115.01. On this one, you have calculate the volume in liters that 67 grams of fluorine gas would occupy under these conditions. So it's an ideal gas law problem where you're solving for volume. You're given the mass, however, not the number of moles, so you're going to have to do a step there to convert grams to moles, 67.0 grams. And then, so yeah, it is an ideal gas law problem. And your first part right here that you can use to get that into moles. And then you can carry that on through and do do the rest of the calculation. Another way to do that would be not to just to solve this part for N, right? But don't take it out of your calculator, and then do these other steps. So get your N, leave it in your calculator, multiply it by this, by that, and divide by your pressure, and then round that. So that might give you a slight different rounding number when you do that. But remember, I will give you plus or minus 1 in the last sig fig for rounding error, if there is any.